MapReduce uses the term worker to denote the thread or process that executes one of the map or reduce tasks. And with one worker per core, we get multiple workers per machine, depending on how many cores we have on each machine. Here is the same picture from before, except that I have overlaid the different task names and grouped the tasks together by machines. So the first group of tasks here might be executed on one machine, and the second group here to be executed on another one, etc. Shuffling is performed automatically by the system, and the final reduce phase is again executed by workers, and potentially with multiple reduce workers running on a single machine if the machine has multiple cores. Now let's discuss some MapReduce implementation details. In this class, we have discussed the importance of fault tolerance and how to recover from failures in relational systems. How does that work in MapReduce? In MapReduce, we read data from the disk, so if a mapper fails, we can just restart a new mapper task and reading the data that it is supposed to process from the disk again. But what about the outputs that the readers are supposed to generate? Since the reducer phase doesn't start until the mappers are all done, so if one of the mappers fail, then do we restart all the mappers from scratch? The answer is no. MapReduce actually writes the mappers' outputs to the disk for persistence. So we don't need to restart all the mappers if one of them crashes. Then, during the reduce phase, each of the reducers reads the files from the disk as its input. And if the reducer crashes during execution, it just gets restarted by the system. And each reducer's output is then written to the disk at the very end. A typical MapReduce or Hadoop implementation has one machine serving as the leader. The leader's job is to accept new MapReduce tasks and assign them to workers later on. The leader also partitions the input file into multiple groups called splits to be assigned to workers. This can be done, for instance, using range-based partitioning on the key value. The leader then starts the map phase by assigning workers to different map tasks. As we discussed, each worker thread can be assigned to a single core. Each mapper then writes its output to the local disk for fault tolerance, as we discussed before. These regions are then read by the reducer workers as the reduce phase starts. And the reducers write the final output to the disk when they are done. Besides fault tolerance, one other interesting detail about MapReduce implementation is how it handles stragglers. A straggler is a worker or a machine that takes a very long time to complete its tasks relative to others. This, for instance, can be due to faulty hardware or too many workers assigned to a given machine. Just like in real life, and perhaps in your projects, these stragglers often cause delay in finishing the entire job. So MapReduce's solution to this problem is to preemptively start execution of the same task using the idle workers and hope that one of them will finish it first. So, for instance, in this case, we have 3 workers here, with worker 3 here being the straggler. So after workers 1 and 2 have finished their tasks, the leader node will assign the task that was assigned to worker 3 to the 2 idle workers. We can do this because, as you recall, both map and reduce programs do not keep state across different inputs. So we can simply ask another worker to start reading the same input that was passed to worker 3 earlier and process them while worker 3 is still running. as long as the workers write their outputs to different files. Now, in this case, worker 2 finishes its task before others. So we just kill off the other 2 worker threads and we are done. Now, the analogy to real life stops here. So please don't try to kill your project partners.